All right, so we're going to get started with Jay. Obviously, Jay doesn't need an introduction. Founder of Kafka, and also his new company Confluent. So I'll let him give an introduction and take it forward. A round of applause, please.
Okay, thank you. All right, so this talk is going to be kind of about what Kafka is for, why we made it, and some of the work that went into it and motivated what we were doing, coming from LinkedIn. So that's where I was before Confluent. So this is going to be kind of like Batman Begins for distributed commit logs, which is maybe not quite as exciting as Batman Begins. So our original motivation was around Hadoop. So this was about 2009 in LinkedIn, and we were adopting Hadoop. And we're really trying to get a relatively complete copy of the data set at LinkedIn into Hadoop. And when we started this project, we thought, well, it'll be pretty easy. You just get the data in, and then we'll spend a lot of time doing really creative things with the data, building out these algorithms and data products on top of it. And what we found was actually getting the data in was really hard. And we spent a fair amount of time on that. And so the initial estimate was, oh, it'll take a few weeks to get all the data, and then after that we'll do the cool stuff. And it turned out, no, this is going to be an ongoing project, and we were going to have like a team of people whose whole job was to scrape logs and aggregate them in different ways. And originally, the way we approached this was really just to kind of gut it out, just deal with the pain. We'll hire people. It'll be a boring job, but they'll kind of do it. And we'll kind of munge each type of data we have, and we'll get it in. And we kind of went through this really because we wanted to get something going on Hadoop. But there was a lot of problems with it. So the first problem was just data coverage. Even with a fair amount of work, we realized we really only had about 15% of the what was really happening in the business, like stuff in databases, what was actually transpiring, what users were experiencing. It was very limited. And each kind of new source system we adopted needed some kind of special Hadoop integration work done. And so it was just this kind of ongoing battle. Every time somebody experimented with something new and exciting, it was like a depressing problem for the Hadoop team. And we were kind of trying to get coverage for each different type of data, and each type of data had its own data format. And then all of these data sources we had were always changing. And then that would break everything downstream, and all the Hadoop jobs would fail because the data had changed out from under them, and it was a giant mess. And so that was really my introduction to this whole problem of data flow and how data actually moves around. And prior to that, I'd done infrastructure work at LinkedIn. I built a key value store and worked on some of the Hadoop adoption and some of the other data products that use data. But I hadn't really thought of data as something that kind of flows. I mostly thought of it as something that would kind of sit in some data store or database, and you might query it, but you don't really think about how it moves around. So it's not really something that moves at all. And when I got into this area, the way I got into it was really kind of just doing an inventory of what we were doing with data in different areas. So I kind of went around the company and tried to determine how we handled each type of data and how did it actually flow. And it was kind of interesting, and it's not that different from what I've seen in other companies. It turns out there was a lot of answers to this question. So for database data that was coming out of relational databases, we had maybe 3 ways of getting that stuff. We were, we're kind of polling for changes, and we had something that went to the data warehouse, and we were dumping out CSV files and copying them into Hadoop. And for our key value store, we'd done something totally custom and sort of ad hoc but scalable. And we had a totally different mechanism for user events. This is kind of what are the users doing. This is the kind of behavioral logging. Here we were kind of aggregating this data, and then we would kind of rsync it around from different data centers and load it up into Hadoop. And if you've kind of been around the block, then whenever you see one of these diagrams that has rsync at some critical stage, there's going to be some pain at some point. And sure enough, there was some pain. The downside of this was it was very batch-oriented, and nobody else could get this user data. We kind of hacked it to get Hadoop in there, but nobody else could get a hold of what was happening. And we had other ad hoc setups for log data and our kind of application metrics. They each went to some special purpose system, and that data was not generally available. And we had some smattering of kind of messaging systems deployed all over. We were using ActiveMQ at that time, but it was really just like this application would have some message brokers, and that application would have some. There was no kind of real central thing. And each of these different, data flows kind of had its own pros and cons. Like they all kind of made sense individually, and they kind of did mostly what they need to. But they all kind of had different pros and cons. So some were scalable, like our log data pipeline with rsync. Rsync is like super scalable. You can set up lots of rsyncs and then and then it scales. But it was only every few hours that data would ship. The messaging systems were pretty real time, but they were had pretty weak guarantees and were not particularly scalable. The database stuff just varied and had pretty poor data coverage. And when you put it all together, it was kind of a giant mess. So we had basically a little bit of each of these things. They were all different. If you wanted to get a hold of any particular piece of data, you had to first figure out how it flowed, if it flowed at all, and then kind of tap into that particular thing. And as the company grew, we kind of ended up scaling each of these data pipelines as its own problem. And as we kind of moved to multiple data centers and needed to kind of scale out across the world, we needed some multi-data center story for each of these things. And the pain kind of grew with the problem. And what I was interested in, since I came from an infrastructure background, was really some kind of infrastructure solution. So basically, I didn't want to grow a big team of people who was doing data integration and log file parsing for Hadoop, right? It's hard to keep that team motivated. The problem kind of scales with the company size. So every time we hired a few more engineers, they would probably produce more data, and we would have to hire some more engineers to parse that data and load it into Hadoop. So it was not a great solution. I wanted something where, like any kind of infrastructure investment, you kind of work real hard at it for a period of time, and then you have something you can reuse a lot. And the idea we came up with was to really have some kind of platform for streams of data. So the inspiration we had was we were pretty impressed with Hadoop and the ability to have something that was kind of company-wide where you could store all your stuff and you could process it. And we thought, well, it should be possible to have something similar for streams. So, if this can be kind of like the offline, warehouse of everything that happened, this could be a more real-time warehouse where data is kind of continuously available. Our interest in that was, being able to really dump all these different data sources. So being able to capture database changes, being able to publish application metrics, being able to compute real-time analytics and reporting off of it, being able to have applications and stream processing systems tap into it, having that be the basis for other kind of derived data systems, and being able to do monitoring off of it. So this was really our kind of big idea was we thought, well, the ideal solution to all these problems would be if we had some kind of platform like this for streams of data. And so then the problem was really just how to get such a thing. Our original approach was to try and build it on top of some existing messaging systems because we were like, well, we don't really know very much about messaging systems, but there's these things out there, and they claim to basically solve this problem. So maybe if we built some layer of coordination or glue on top, we could have that be the implementation. So we spent actually about a quarter trying to play with this and see what it would look like if you did real kind of production load with large data on top of something that was on these. And we found it was actually really hard. It was actually not going to work out. So overall, the throughput for the messaging systems was not really good enough to support high volume log or activity data. None of that data individually is that valuable, and if you're going to actually capture it and make it available, you have to have something which is cost effective. So in particular, it looks suspiciously like we would need as many ActiveMQ servers as we had other servers if we wanted to go down that route, which is not going to work. None of these systems did a good job of integrating with kind of our batch ecosystem. None of them did a good job of persisting data, which is important if you want to be able to really buffer everything happening in a company while your Hadoop cluster is down. And none of them actually had kind of ordering or storage guarantees that were really appropriate for any kind of database changes, the kind of things we would put into our search index where you really have to end up with the right answer in the search system or the customer experience is not great. So our second attempt at this problem was to build something from scratch, and that was how we came up with Kafka. And I'll give kind of a brief overview. It sounds like some people are already kind of familiar with Kafka. For people who are not, this will be a very brief introduction. Kafka itself is pretty simple, so it doesn't actually take very long to explain. So it works kind of like a messaging system in that there's a Kafka cluster. There's processes which send messages into the cluster. Those are called producers, and there's processors which read these streams of messages, and they're called consumers. And in that respect, it's pretty similar to a messaging system. And really, the difference is kind of like in the core abstraction it provides to do that, which is actually quite different. So Kafka is built around this idea of a log, which is basically a sequence of records. So each of these rectangles is meant to be a record. And in Kafka, they will each get some kind of sequential number like 0, 1, 2, 3, 4, 5. And the new data is always appended at the end of this log. And then you can have different readers, which are kind of at different points in time in this log, and they kind of read from left to right. So that's kind of the core abstraction that Kafka provides. And it turns out that this is a pretty valuable abstraction. It's not clear how it's related to messaging or message systems until you actually see it work, but it actually does exactly that. So if you have some source system, maybe an application which is publishing writes of data, then you have these different application systems which are reading off of this log. And the core idea in this is that these readers, they actually control the pace that they read at, right? So they get to control how they advance, how quickly they advance. So you can have a batch reader which kind of wakes up once a day, and maybe it's at record 7 and reads up to the head of the log and goes back to sleep, and then maybe it wakes up again at midnight and does the same thing, and it does that every day. And that's basically batch processing, but I guess now off this log. But you can also have real-time processing where you have a process which continually reads and is right at the end and is up to the millisecond, right? And so this kind of idea allows you to kind of unify these batch uses of data which are periodic with real-time uses of data. And that's kind of the core thing you get out of this abstraction. And it also makes the consumers of data very cheap. So all a consumer needs to do is kind of remember its number for one of these logs. So it remembers that it's at record 11. And that's kind of the only impact other than the disk I/O of actually reading the data that a consumer has. So unlike traditional messaging systems, we don't write one copy of the data for each reader. Which would be ridiculous if you had many readers and a lot of data. We just have one copy of the data, and everybody has a pointer into that, which actually makes a lot more sense if you think about it. I don't know why the other systems work that way. And so the core abstraction in Kafka is what we call a topic, which is basically a collection of these logs. And this would represent some feed of data. So for a website, it might be all the clicks and all the impressions of things and the searches. In finance, it's something totally different. In retail, it could be sales and product arrivals and shipments and anything with logistics. There's routing and position information. So the actual events or records you capture, of course, they're totally specific to your use. But usually a topic would be some grouping of everything in a company that is related to that subject. So at LinkedIn, we would have a page view topic, which was every HTTP request to the website, basically every page that was viewed. And each of these individual logs is spread over the Kafka cluster and replicated for fault tolerance. So you can have one of the Kafka servers can die, and the other replicas will take over responsibility for that log. So the outcome is that question. Yeah, so the question is whether, I'm not going to repeat the questions because there's a streaming stuff, but the question is whether one record can be in multiple topics. The answer is only if you put it in multiple topics. So if you write it here and then you write it there, then it's in both, but if you just write it to one, then it's just in the one. So there's not, in some sense, there's not a pointer from one topic to the other or anything like that. So the end result is you basically have something which is meant to look like a modern distributed system, meaning you operate it as a cluster. It is distributed by default. You think about writing to the cluster, not writing to an individual machine. You can kind of expand it out, and you can handle fault tolerance internally. It has a built-in partitioning model, kind of all the things you would expect of a modern distributed system. But one that is oriented around streams of data instead of static tables or whatever. So that was really what we were trying to do. In particular, we wanted to be able to provide kind of cost-effective scalability, so you could have many terabytes of data per machine and hundreds of megabytes per second of throughput, as well as strong guarantees. So it was important for us that we be able to use this across all these different data types that I described, right? So if you want to handle the big, unimportant data, you got to be cheap. And if you want to handle the important stuff, you have to be right, right? And so it's important to be both cheap and right. Otherwise, you're kind of inherently forking off into different systems. And in terms of guarantees, the guarantees that are going to be important are, A, that you have a real, notion of committing a message and when is it actually written across replicas and when do you guarantee that it won't be lost if one of those replicas fails. And then also that you maintain order for these messages so that if you're tracking database changes, for example, it's not legitimate to reorder database changes. That's actually going to give you different results. So it's important to have some guarantees around order all the way through to the consumer, which is another kind of knock on some of the messaging systems is they don't necessarily do a good job of that in the presence of scaling. So this was kind of really the system characteristics that we came up with. And this ended up being, at LinkedIn, really, there's kind of stream platform. This was the place we could dump all these streams of data kind of as they happened. And it kind of united these different data types in one area. It was the primary feed of data into the offline environment. And so that really kind of solved this problem of getting all the data around to different things, getting it into search systems, getting it into Hadoop, getting it into key value stores. And as we had been building this, we had a second use case in mind that we were thinking about and planning for that was a little bit more of like a hypothesis than like really a requirement, if that makes sense. And that was being able to use these same feeds for stream processing. So we felt that like, hey, we have almost no real-time data available. And we also have very few things that process data in real time. But we thought, well, if data was available in real time, maybe we would process it in real time. It kind of makes sense. Like if you think about most companies or businesses or whatever, they operate 24 hours a day. They generate data 24 hours a day. It kind of makes sense that a lot of the like analytical processing and use of that data would also be continuous. But actually, a lot of it happens in batches. So we thought, well, if we could really like make this platform work correctly, and if we built it to support this from the ground up, we could actually have a pretty good ecosystem around real-time stream processing. So this was our other kind of hypothesis, and it actually turned out to be quite true. And the observations I would share about that are a couple. This is kind of what I think we learned. First of all, if you're collecting data in batch, if data in the organization is only available in batch, you're going to process it in batch. It's kind of obvious, but like, there's no point if you collect data at the end of the day in processing it as a stream. Like, it just doesn't add any value. So you actually have to have this type of continuous stream of data available to be able to have any kind of stream processing or to have that even make any sense. So basically, we had to do Kafka before we could have any kind of stream processing ecosystem. The example of that I sometimes use is basically the US Census. So if people, people are probably familiar with the US Census. Every 10 years, they like go around with binders and they write down everybody who lives in every house. And then they take all the binders back to Washington, D.C., and they count them all up, and that's how many people there are. And of course, the answer is basically wrong by the time you finish counting. But it's kind of, if you think about it, it's kind of a weird way to keep that tally. Like you would imagine, recording when somebody was born or when they died, and when they kind of came into the country or when they moved out of the country. And you would imagine just keeping a running tally, and that would be how you would keep track of how many citizens you had in each area or whatever. But of course, you can see why it works the way it works, which is when they started taking the census, they didn't have that capability at all. They basically had horses and binders. And so the technology the census is built on is horses and binders. And to a certain extent, I mean, I think a lot of kind of analytical data processing is still in that like horses and binders phase where you kind of go around all the systems and you dump out what they have, and then you kind of run a big job on it at night that kind of churns out some results. And I think if you think about how modern businesses work, it's a little bit more real time than that. Like if you look in there, I don't know, they got all these beautiful looking graphs moving left to right. It's a little bit more real time, right? And so being able to support that with data, I think, is important. The second observation that still isn't obvious to people is that this area of stream processing can actually be quite powerful. So a lot of the early stream processing systems were kind of weak. They would get incorrect results. you would kind of struggle to keep up with the flow of data. They were approximate and kind of lossy. That is not inherent in the problem. That was just like limitations in those systems. And I think you're actually seeing a ton of activity in this area of real-time processing of data, and they're getting better and better. And so, I would actually expect that, the way we're going to see this in a few years is that really stream processing is a type of generalization of batch processing and request response processing. And I'll say a little bit about what I mean by that. So people are mostly familiar with like request response processing. This is, I give you an HTTP request, you give me back an HTTP response, right? Or I send a database request, you give me back a database response. So you get one input, you produce one output. Batch processing, this is your cron jobs or your Hadoop jobs or whatever. This is, you kind of have a bunch of inputs, you kind of process them all, you produce a bunch of outputs. And stream processing, at least in the way I'm defining it, is basically kind of a generalization of these two things. So, the program now gets to consume some inputs at a rate it describes, right? It gets to kind of read from that log and consume some inputs, and it produces some outputs, and it gets to choose how much. So it could be very batchy, and it could kind of consume everything and produce all its output, in which case it's basically kind of a degenerate stream processor that's really a batch processor. It could do one at a time and produce an output for each input, in which case it's really kind of a degenerate stream processor as a request response processor. But it could actually do anything in between those two. And so in that sense, I think it's actually a pretty powerful model. And I think thinking about programs in this way, I think is actually a pretty interesting way to think about them. And kind of in my world, I would say basically these stream processors are really, it's kind of a program that's transforming these Kafka topics. So a Kafka topic is kind of one of these streams of data like page views. You can basically produce some program which can run in a distributed fashion and transform that into a new topic, which could be transformed into other topics, which ultimately end up somewhere. And everybody is kind of probably at least a little bit familiar with this programming model from like Unix pipes, where you have, programs that can read input and pipe them into other programs without necessarily knowing about the program on the other side. And there's a fair amount of work happening on frameworks in this area. So I would say, actually, this is a partial list. There's more happening here. So there's kind of an embarrassment of riches in the stream processing space. And kind of the way I would think about it is Kafka is basically providing some stream of data. These frameworks are kind of allowing you to build applications that do processing. And if you put it together, you get some kind of stream processing. This is the only mathematical equation, I think, in this talk. So when we put this together, this is kind of the resulting architecture for LinkedIn. We were able to capture events out of applications. We were able to capture application logs, metrics, kind of everything that was happening there. We were able to capture changes coming into databases, all as kind of streams. They all kind of looked the same. They had the same data format. They were all kind of available in this streaming platform. And those were then available to kind of real-time monitoring systems like log search or monitoring, or the whole security area kind of looked at this data and looked for bad patterns, or we had a whole kind of real-time analytics and reporting, actually a few systems in that space, as well as being available for applications that were asynchronous. So all the data feeds that would go into the home page on LinkedIn that has all the updates, or emails, or any of that kind of asynchronous processing would all go through this, either applications or the stream processing framework that we had there. And then that would basically publish back derived feeds. These derived feeds might go out to live serving systems, or they might go back down to Hadoop in the warehouse area. And pretty much everything in this area, whether it was a kind of primary data we captured or a derived feed, was available in Hadoop for kind of offline retention. And so we kind of got away from that like horrible mess to something that was kind of a central message bus across the company, which spanned all the data centers and kind of unified this whole mess of different systems and applications together. And over time, the usage at LinkedIn became pretty large scale. So we kind of got every different type of data into the system. Nowadays, it's actually handling over 1 trillion messages every day. And more than that being read every day, because, of course, it's multi-subscriber. So anything you write has at least one reader for Hadoop, and usually a few more. Overall, there's over 1 petabyte of data in the Kafka clusters. And there's tens of thousands of processes that are connected and producing data. So in fact, pretty much every process at LinkedIn would connect at least to produce like logs and metric data. And this was kind of the backbone for a lot of the core data systems, like the search system and the social graph system and the newsfeed. They would all kind of get their feeds of data through this central pipeline. And it got adopted as we open sourced it. It got adopted by a bunch of other companies. So it's used in production kind of all over the place for really kind of the similar use cases to what I described and some pretty exciting new stuff. And as this started to pick up usage, at LinkedIn and then outside of LinkedIn, we realized actually this is a pretty deep change in how people use data. Like we were kind of moving to this very real-time model of data. We thought it was a really cool thing. And we thought it could be a really big deal. So we ended up leaving LinkedIn, the team that built Kafka, and we started this company Confluent, which is where I'm at now. And we're really basically just rebuilding an open source platform that replicates what we had at LinkedIn, which is built around Kafka, has some tools for managing schema for data and dealing with how you evolve your data over time. We're building out a set of connectors for common data systems to plug things in and monitoring tools across this. And so I said I would give just kind of a brief overview of some of the upcoming stuff. So we have a open source release for Apache Kafka, which should be happening towards the end of November, and that'll be followed pretty quickly afterwards with this Confluent platform release. And the Confluent platform is kind of like Kafka plus goodies. So we're kind of, here we're basically trying to package up a lot of the other open source tools that are available. So the stuff that is coming in Kafka is security. So finally we have SSL and Kerberos and client certificates to authenticate, as well as like an authorization system that gives you permissions on a per topic basis. So this is really important in larger companies that need to have more granular security and permissions across data. We've added quotas. So this is the ability to enforce certain throughputs on a per application basis. So you can say, okay, this application is entitled to 100 megabytes per second. This application is entitled to 150 megabytes per second. If an application exceeds that throughput, it will be slowed down to that rate. And the reason for both security and quotas is to help with this kind of large-scale multi-tenant usage. So the usage I described where you have lots of things plugging in, you want to make sure that people can only get at the data they're supposed to get at, and you want to make sure that one misbehaving application doesn't bring down the whole cluster in some way. So if you have one person who moves their logging inside the for loop or whatever, you don't want that to absorb all the I/O that you have in the entire cluster. So those features are going in. We've basically redone the consumer. So this is kind of infrastructure work, but we've been reworking the clients. So we redid the producer a few releases ago. Now we've carried that out to the consumer, and we've added a whole framework on the server side, which helps to manage these consumers. So we were previously using Zookeeper for that, and now it's like a native Kafka protocol. And this makes it a lot easier for us to have high-quality consumer clients in other languages because they don't have to interact with Zookeeper. It also makes scaling the consumers a lot easier. So this new consumer kind of replaces the existing consumer APIs. It kind of has all the features people were getting out of the high-level consumer, like failover and load balancing, but it also allows you to do the things that kind of lower-level consumer APIs were doing, like go back in time and reconsume things. So if you've been using Kafka already, this should actually solve a lot of the kind of complaints people have about the consumer, either feature-wise or scalability or whatever. So the next thing that we've put together is this connector framework, which actually also relies on this kind of consumer group management feature. But what it does is actually allow you to connect other systems into Kafka. And so at least the working name for that is Copycat. We may come up with a different name before they release if we can think of something better. But what this allows you to do is tap into, say, database change logs and have a plugin for that, tap into Hadoop and produce data maybe into that, or Elasticsearch, have these different plugins for different systems and run them in a common framework, which kind of helps to scale these out, helps to monitor them, does the fault tolerance. So what we're trying to do is basically get a good library of these connectors and a good way to run them and monitor them that's all common, so that plugging lots of things into Kafka is really easy to do. So if you're trying to do that work of hooking up stuff to Kafka, this is super relevant to you. And then stuff that we're including in the Confluent platform is a lot of the connectors that go with that framework. These are kind of federated. They're not all going to be part of the Apache Kafka project. There's external ones coming from other companies, and there's open source ones. And then we're starting to build out the library of clients. So historically, Kafka has just maintained the Java client with the project. But, and that meant, the clients in different languages have been, like, I would say, of uneven quality. Some are very high quality, some are very low quality. So what we're trying to do is get really high quality clients across all the different languages. So we're adding into that the C client, which is very good. We hired the guy who did the C client, and we're going to start adding, additional clients for all the languages and try and bring them up to feature parity with Java and make sure that they all get tested together and so on. And that's it. So if you're interested in this stuff, we have a pretty active blog, which is blog.confluent.io, and you can check that out. There's lots of blog posts. I've done like a long blog post on logs, which kind of goes more into the details here. Which there's a book version of it too, if you like books better than blogs. And Kafka itself, you can find at that address. And that's all I had. I'm super happy to answer questions if people have them. I know there's kind of a mixture of backgrounds with Kafka, so for some people this may be stuff you've already heard many times, and hopefully you learned at least one new thing. Question? Yeah, okay. Mm-hmm. Yeah. Yeah. Great. Okay, so the question was just kind of a general, message format, compatibility, standards around messages, how should that all work? It's a fantastic question. So I totally just glossed over that whole area here. Kafka itself is like schema, free. Basically, the data model of Kafka is you have a key, which is a byte array, and a value, which is a byte array, and that's that. However, data has schemas. Like data has some structure and meaning, and if you just rely totally on a handshake agreement between people to make sense of it, actually it doesn't work that well in this setup. And the reason it doesn't is kind of the picture I showed where you have this kind of company-wide thing where people are publishing streams of data that gets used all over the place. You don't really even necessarily in the end know all the users of your data streams. You often have shared data streams, like a page view is something which is produced in many applications. And it turns out even iPhone apps at LinkedIn, even though I don't know what a page view is in an iPhone. But anyhow, it exists. And so how do you keep all these people producing correct, high-quality data across a large organization without slowing everything down and having some kind of horrible data schema committee that agrees on everything? I think that's a really interesting area that's worthy of a lot of discussion. It's a problem most people find much later on. So they first get a lot of stuff going, and then later they realize oh my God, everything that depends on data breaks once a day roughly because somebody produces bad data or whatever. We did actually do a lot of work at that on LinkedIn. We're basically replicating a lot of that for Confluent. People's opinions on this kind of are all over the place. Some people, I think it's almost like a personality test. So some people are in favor of freedom, and they're just I got to be free, man, and I'm just going to put my JSON in, and sometimes the JSON will be bad, and you just got to deal with it. But if we all try, it'll be good. And other people are more bondage and discipline, right? And they like schemas. So I actually started in the first category, and over time I basically migrated to the second category as I watched how it played out at larger scale. So, so for people who are willing to invest a little bit in it, we do actually ship with Confluent Platform this schema registry. What it allows you to do is associate with each of these Kafka topics an Avro schema. So it depends on Avro, which is kind of like a binary format for JSON if you don't follow the wild world of serialization libraries. And that schema basically denotes all the fields that you're expecting. What's their data type? Are they required? Are they not required? And what we did that I think was interesting or unique in that area was do this in a way that explicitly thinks about how schemas will evolve and make that really automatic. So kind of the reason I think people don't like schemas is actually because the evolution of schemas has not always been well handled in all databases. And so they've been bitten by databases that make it very, very difficult to upgrade your schema as your data needs to evolve. And then their result is like, well, I want no description at all. I'm just going to manage it myself. The problem with that is in that very distributed environment, you actually do need some contract. Even I, as a producer of data, want to know if I'm fulfilling my contract to the many applications without having to like test each one of them every time I change something. So the way we did this is we actually, instead of just thinking of a schema as something you have right now, you think of a schema as something that evolves over time. And then you can have rules about what types of changes to schemas are compatible or not compatible. And you can say, well, OK, for this topic, it's Wild West. Do whatever you want. We don't care. For this topic, we're going to allow evolution, but it actually has to be backwards compatible, or it has to be forwards compatible. And those things mean, backwards compatible and forwards compatible. Kind of the meanings are, can I read the old data using the new schema? And can I read the new data using the old schema? And the reasons you might want both of those is, one, if you have a bunch of old data in Hadoop, you probably want to be able to query against it as if it were the new table definition. And if you have an application which was built last week, you probably want it to still be able to handle data which is the new data as of this week. And so you need that kind of both direction compatibility for different uses. If you do this, I think it basically gets a lot of the coordination out of how you evolve data. You suddenly have this nice description that everybody can comment on in code review and say, OK, I think this field should be named this, and blah, blah, blah. And then you can just kind of go and have it actually carry out all the way through. We did this, and we did a good job, I think, of integrating it into Hadoop and the load into Hadoop so it could kind of carry through transparently to Hive and that kind of thing, so that each Kafka topic would correspond to a Hive table. The fields would carry through, the types would carry through. If you created a new Kafka topic, you didn't have to like file a ticket or something. It would just load into Hive automatically. So I thought we got a ton of mileage out of that. I think ultimately, I guess I personally and Confluent are not particularly committed to any serialization approach. I mean, people will do what they'll do. But I think at least for a larger organization, you can get a fair amount out of that. So that's why we took the time to try and get some of that stuff built out into software for people to use. Yeah. So what we're doing, that's right. So the stuff we built basically works with anything, but we're trying to at least provide one good option out of the box. Question? Yeah, sure. OK, so the question was, what is the Kappa architecture, and is it a joke? And the answer is, it is kind of a joke. OK. So I'm gonna show one of these log pictures because it kind of helps. So like right now, people are trying to work through a lot of the details of how to make a robust stream processing application. And it turns out there's like a lot of hard problems you have to solve, and they're kind of like, I would say 20% solved right now for you in the frameworks. So the problems tend to be like, how do you model time? This is like a big issue. What do you do if like your code changes and therefore you want like all your processing of data to have been changed? How do you handle like back pressure between parts of the system? There's just like a ton of issues, and they're all being worked through. So one of the big ones is, what do I do when my code changes? Right? So let's say that I'm a stream processor and I'm producing counts of page views. Maybe that's what my stream processing job does. And at some point, somebody decides, oh man, we forgot to exclude crawlers from our count, and bots or scrapers or whatever. And we have to go back and redo this count. So they put into their stream processor code, exclude crawlers. The problem, of course, is it's only going to happen going forward. So all your counts are like wrong. If you want to be able to go back and reprocess that, how does that work? And so, there's lots of ways you can do this. One approach is, basically recompute the counts somewhere else, like in Hadoop, and ship them out, and somehow try and integrate that in whatever serving layer you have for counts. The problem with that is it just tends, if you're trying to build an application that does that all the time, it's kind of complicated. And so that would be called the Lambda architecture. I think there's an alternative approach, and this is sort of what we had in mind with Kafka, which is, so I wrote a blog post about it. which is really just actually be able to take your stream processor, which is here, rewind it back in time, and replay it. And it could even be run in parallel to the existing stream processor. So you could start like another version of that that's recomputing. Obviously, to do that, you have to retain the data you're going to want to reprocess. But the advantage of that is it's relatively simple. So if you write something which is processing off of this stream, it's the exact same program running off the exact same system. You basically just rerun it. And so infrastructurally, it's a little simpler. I think this argument is kind of, both approaches are good. Neither is actually really built out for you well in software right now. So it's more of a theoretical discussion, I would say, because until I get one of those solutions really built for me in software, and I'm kind of like doing it by hand if I'm building a stream processing app, I would say that's pretty much a bad situation no matter what. Whichever of those two approaches you're doing by hand, you basically shouldn't be doing either of them by hand. The framework should come with built-in support for kind of reprocessing data. And I would say most of the frameworks don't do a good job of that actually in either approach. So like in this stream processing area, expect in the next few years a lot of these like pain points to get ticked off to the point where you actually have a pretty robust framework that handles some of the hard problems, and I would expect that to be one of them. Question? Mm-hmm. Mm-hmm. Yeah. So the question is like, I'm going to kind of interpret, but I think the question is basically, does that make sense to store data in Kafka, right? If it's kind of like a messaging system, then do you really want to be like storing data there? Is that like good? And the answer is like maybe, I would say. So here's what I would say. It was definitely designed to store data. So it stores data in files, it replicates them. There's like basically a bunch of hard problems you have to do if you want to make that work. And we did those hard problems because we wanted to make it possible to like store data and reread it. The second part of that answer, I think, really depends on what systems you're good at operating. So like if you have some source of truth store you're really good at running and it's not Kafka, then maybe you should put your stuff there for long-term storage, right? Or whatever. So I guess to be effective as kind of a long-term store, you have to be good at running it so that it doesn't go down. But there's no like architectural reason that it's bad to keep data in Kafka. And Kafka has a retention setting which controls how much of this log is saved. And so there's no architectural reason it would be bad, I think, to do that. And that's certainly a use case we've tried to design against, and it's certainly something people do in practice. Questions? Mm-hmm. Yeah. So the question is, how well does Kafka deal with data centers? And so the model, I didn't really get into that in this talk. Most people who use Kafka use it in like a multi-data center environment. The model we support is actually having a Kafka cluster in each data center, and you can like mirror between them. So unlike a request response database, you're not really looking for like global synchronous writes across the world, right? It is like a feed. And so I think that model where you basically have a local Kafka cluster in each data center actually works pretty well. Like in each data center, you write to that cluster. If the connection to the rest of the world goes down, you can still write to that cluster. You're not losing data. The things in that data center just read and write from that cluster. And then the mirroring between data centers, you kind of control on the back end. And that way, it's kind of more administrative how data flows. You kind of operationally control that. Yeah. So we have this tool called Mirror Maker, which basically does mirroring. And you can mirror like star, which would be all topics, or you can do star, but not this blacklist, or you can do a whitelist, or you can kind of combine. So you have some flexibility there. Yeah. So right now that's right. Right now we don't do multi-master, so you need to have some kind of like, if you want to mirror many things into one Kafka cluster, you need some kind of like aggregate cluster. We'll probably add that in the future, but I don't think there's like a crisp timeline for when we'll have it. Question? Mm-hmm. Yeah, so the question is, are you planning on adding real-time ETL on Kafka? And I guess the answer is, I think, yes. I think the usage of such a thing is actually a lot more than ETL. I guess it depends on the definition of ETL, but for people who don't know, ETL is like extract, transform, load. So this connector framework I described is kind of extract and load, right? So it's how you would connect a database or something to Kafka to capture a stream of data, or how you would get it back in. It doesn't do any transformation. That's by design. The transformation you can do with these existing stream processing systems, and we're actually working on adding like a native transformer, DSL and client to Kafka, which I think is probably our best answer to how to do that kind of continuous transformation. And I would say that combination is probably what you mean by real-time ETL. Mm-hmm. 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 Well, so it's at least EL. Yeah. Yeah, sure. So, so the question is, what is copycat? I described it as that connector framework. I didn't give it the name copycat because right now I think people are arguing over what the final name should be. So currently the name is copycat. What it does is, here's what we've noticed. Like, oftentimes people will have 100 relational database instances they want to plug in, some distributed key value stores with lots of partitions, a Hadoop cluster, and Elasticsearch. And they basically want to be able to plug all these things into Kafka in one direction or the other, either as a source of data or as a place you want to get data into. Copycat is basically there to make a very simple API for writing plugins to these types of systems, and do it in a way that you can scale out that data load or unload over a pool of processes and have them be fault tolerant and so on. So that's what it does. You would basically write a Elasticsearch plugin, and then you can run that over a pool of these processes. This same pool can basically do multiple of these connectors. So it could run the data load into Hadoop, as well as the data load out of Hadoop to deploy out to live data centers, as well as the load into Elasticsearch. And so our goal in that is really to unify the few hundred odd Kafka, ad hoc Kafka connectors that are kind of out there on GitHub. Like, there's a bunch of these things that connect up things to Kafka, but they're all kind of work differently, and a lot of them don't really have a scale-out story or any fault tolerance, and they're all monitored differently. So we wanted to basically make some common framework that would make running a lot of these like much easier, and that's what copycat is. Does that answer your question? Yeah. Yeah. So the way the question is, how can I like transform data that's being loaded with copycat? The answer is not with copycat. We're really trying to decompose the problem into two parts. The first part is how do you integrate data streams with Kafka? The second is how do you do transformation on top of that? Copycat will let you do simple things like filter out fields on messages, but if you want to do richer stuff like join together different data sources and munge it in some way, that I think is really a stream processing problem. And so then the answer comes back to how do you do stream processing? Well, you can do it in a custom application. You can do it in one of the 5 odd frameworks that are out there. And I think we're adding basically integrated processing capabilities, which I guess is our best answer to that question. All of those work well on top of Kafka. So you kind of get to choose the tool of your choice. Question? Mm-hmm. 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 Yeah, sure. So I guess I would say all these stream processing frameworks are kind of a tool to help you build a stream processing application. So all those things I put up there, they're basically all Java frameworks. There doesn't seem to be much out there outside the Java universe. They're aimed at hopefully providing you some higher level interface to processing streams of messages and doing that. Samza was a framework we built at LinkedIn that is basically built on top of Kafka's primitives for streams. So it's actually very small. I think the whole thing was like, maybe 7,000 lines of code or something. We're actually redoing that work and integrating it with Kafka. So there's this initiative called Kafka Streams. It's basically like Samza 2.0, I guess. It maintains pretty much the same processing model. It adds the ability to have kind of a rich graph of processing, and it adds a higher level DSL on top of it, which I think makes it a lot more usable. and it gets rid of the dependence on Yarn, which Samza had, and it uses this kind of native group management facility that we added in Kafka that Copycat also uses, that the consumer also uses. So this is our kind of approach to managing pools of processes. So basically, we just kind of went through the list of problems we saw in Samza, and we kind of corrected those and made like a higher level interface, and that's what we're integrating, which is called Kafka Streams and should be out kind of early next year. But I guess the way we're approaching stream processing stuff is like, it's kind of a big happy family. Like there's lots of these tools. They're all about 50% of what you totally need in the end state. And we'll see how far they all get. But right now it's kind of an embarrassment of half-finished dishes, I would say. Question? Yeah, sure. So the question is, what about Voldemort and Azkaban? So these were other open source projects that LinkedIn had that I was also involved in. So Voldemort was a distributed key value store that was really an Amazon Dynamo clone. And not like DynamoDB, the new thing, but like old school Amazon Dynamo. So I wrote it at LinkedIn. It was the first piece of infrastructure programming I did there. I learned a lot in doing it. It's still run there at massive scale, actually. It serves a ton of stuff there. Some adoption outside of LinkedIn, I wouldn't say like massively adopted. We didn't really continue like pushing on the feature set in the way I thought like Cassandra and other systems did. We mostly just focused on like operability. LinkedIn actually had a second generation kind of key value store, distributed database that was meant to do a lot more. It was probably more like a probably better built version of MongoDB or something. That had kind of a richer set of queries and integrated schemas and kind of a lot of the features that are missing in a pure hash table. Azkaban was a workflow scheduler that we ran all our Hadoop stuff through. So this was a way that basically pretty much all the teams interacted with Hadoop from a production standpoint. So you would basically make a job that was some graph of Hive queries or pig jobs or MapReduce things, and you would basically upload it to the central scheduler, which would kick it off at a certain time and then run the whole dependency of jobs like, hey, first run this, and then run this, and then run this, and then run this. And that's really important if you're trying to make production Hadoop workflows. Shortly after we wrote that, this thing Uzi came out of Yahoo, which is very similar. I don't know if it's good or bad, or if it's better than Azkaban or worse. All right, that's what I like to hear. Yeah, so I worked on the first version of Azkaban. Then some people came in and rewrote it much better, and it has all these like graph visualizations and stuff. So I don't know as much about what it currently does, and basically anything good in it, I can't take credit for. Anything bad in it, I probably still can't take credit for. So I don't know. All right, other questions? No, although many people have wanted me to say that. So the question is, will Kafka get rid of its dependence on Zookeeper in the 0.9 release coming up imminently? The answer is no, it will not. What it will do is it will remove the client interaction with Zookeeper. So originally both the producer and the consumer in Kafka would use Zookeeper to locate the nodes in the cluster and figure out which partitions were there and balance load, and the consumer would save its offset there. And what we realized in running this at large scale is, and this is like contrary to everything you would hear. So people really like this pattern where everything connects to Zookeeper, but we found Zookeeper to be very hard to operate in a world where you have like 10,000 processes interacting with it. And we also knew going in that our use of it as an offset store was basically bad. So over time, we realized we had to walk that back if we wanted to have scalable answers to many of those problems. So the first thing we did was we removed all the use of Zookeeper for metadata from the client. So that's been gone for several releases. The next thing we did was we got rid of it for saving the position of the consumer. That can be a very high write load, and so it was like an important thing to get it out. So that's natively stored in Kafka, which is really good. It allows you to kind of horizontally scale that with the cluster, which obviously you need to do. The final piece of that is managing these pools of consumer clients, managing pools of copycat processes, and managing, in the future, pools of stream processors, or I guess pools of anything you want that's going to process stuff. And to do that, we basically, in the existing consumer, it's connecting to Zookeeper to do that. We basically added a native protocol in Kafka that does that. That, again, allows it to scale out with the Kafka cluster. It's actually much more efficient as well if you're consuming lots of stuff. So if you use the existing Kafka consumer, the high-level consumer, as you add more and more things you consume, it can get a little bit slow to rebalance data when things fail. And so that goes from being very slow to being very, very fast with this native protocol. And it actually allows us to generalize this support to support all these different uses. So that's happening. At that point, all the quotaing and permissions and interaction with clients all just goes through Kafka, and the Zookeeper stuff is really an implementation detail of the cluster. So from an operability point of view, that's awesome, mission accomplished. Now, some people just hate Zookeeper. Those people are still unhappy because it's still there. It would be nice to have that stuff kind of done natively in Kafka, so there was only just one thing you deployed. On the other hand, Zookeeper is relatively hard to write, and so you also want it to work correctly. So we haven't bitten off that problem yet, and I'm not sure when we would, but it would be nice if there was no Zookeeper dependency, but there's no clear roadmap to that. Some people have asked to make Zookeeper pluggable, so you can plug in things that are a lot like Zookeeper but aren't, like etcd, or there's I think a few of these things that are kind of like Zookeeper clones. I'm not super interested in doing that just because I think it's very hard to make pluggable work in a way that's actually reliable and gets tested in every way and so on. So I think the next step would be get rid of Zookeeper, but we don't have a clear timeline for doing that or a design for how it would happen. Cool. Question? Mm-hmm. Yeah. So the question is, how does Kafka compare to Kinesis? So it's a great question. They're very similar. I mean, I think Kinesis is modeled on Kafka. Kinesis is a hosted service. It's proprietary. It's only available in AWS. There's probably a few ways in which Kafka is better. It's much lower latency. It does a much better job of batching messages together. So if you have high throughput producers, it will actually be just, it'll seem to be like a bazillion times faster. And it's actually just because we're cheating and batching together data and compressing it and stuff before we send it. But nonetheless, it appears to be infinitely faster for that reason. It's faster from the point of view of producer to consumer. There's a whole feature around log compaction and mutable data that is only available in Kafka. You also get kind of full control over how long you retain data for and that kind of thing. So there's a bunch of those features. So I guess the answer is high level, very similar. In terms of the individual details and latency and throughput and that kind of thing, very different. As a hosted thing, of course, Kinesis has pretty tight restrictions on how long you can retain data and how big your messages can be and how much throughput you can get per shard and all that kind of stuff. So you would pretty much have to get into all those details. I think we have some info on that we could probably share if that's helpful. Question in the back. Mm-hmm. Yeah. So the question is, what about storing messages in HBase or something? So I assume you mean, couldn't you use HBase basically as Kafka? Is that kind of what you're asking? Yeah. So theoretically, you could build some kind of publish subscribe mechanism on HBase. I think it obviously has a client which allows you to write. You could kind of maybe poll for changes by some timestamp key or something, or HBase has a log, and you could kind of try and scrape that log. I think in practice, it just isn't very good for that use case. There are people who use it for that, but I think it's just a matter of focus. It's just basically much better. It's going to be more inefficient to do its kind of internal compaction and stuff on data that it does to do all the things HBase does that Kafka doesn't. But the result is, I think it's just not. It probably wouldn't be a great Kafka implementation. So I haven't seen a ton of the where the two, where anybody really wants to do that comparing the two. But you could. I think I guess I would say the more flexible the database is, to a certain extent, a very flexible database, you can actually, like a relational database, you can actually build a great many data abstractions on. but some of them won't be very good. You know, like in particular, I think most of the stream or event-driven processing won't be very good. Like the latency will be bad. You'd probably have to poll for changes or build everything as a trigger or something. So you know, I guess the advantage of some kind of specialized system like this is really you kind of focus on that domain more specifically. All right. Let me do one more question, and we'll take anything else offline. I'm happy to answer questions for a few more minutes, and then I'll get out of here and go to the airport. Question? Yeah, so the question is, you know, you claimed there was some way to kind of hold writers to some throughput. How does that work? Does that mean you're like dropping these people's messages? Like what happens? That's a great question. So the way it works differs depending on whether you're a producer or a consumer. So internally, the way the server implements this is it basically tracks the bytes per second that are being sent to a particular application, even over many connections, right? And as you start to exceed your throughput, what it does is it calculates how much you would be exceeding your throughput in that window if you continued at that rate, and it slows down each request you make by an amount, which brings you to your correct rate. So, you know, it's kind of like cruise control, right? It's dynamically trying to slow down your request to match your target rate. And so on the server side, the implementation is the same no matter what, which is just we calculate the bytes per second coming in on your requests, and we slow down requests to basically bring you to the particular rate. Now, your question is great. What does that actually do from the point of view of my clients? Well, it depends on if you're a producer or a consumer. If you're a consumer, you're basically reading messages sequentially, and you get them slower, right? You actually don't even know you're getting them slower. I mean, maybe you do. Maybe if you knew what you got yesterday and you turn on quotas today, you know it's slower. But you know, the application, it doesn't get an error or anything like that. It's just that it feels like it's reading as fast as possible, but as fast as possible just isn't as fast as it used to be, which is great. On the producer side, what does that mean? So on the producer side, you'll see a similar effect, which is basically your requests are just slightly slower. How does the producer handle that? Well, the way the producer works is as you send messages, it basically adds them to this buffer, which kind of buffers them up. And it tries to send out requests based on that buffer either as fast as possible or with some kind of pre-configured delay that you give to try and batch more. So if you slow down its ability to send data, that back pressure creates more and more batching. At a certain point, you exceed the buffer you have on the producer for batching messages. When that happens, you have two options. You can configure the producer to block, meaning when you go to send, it's just like, oh, I can't get any more in, I'm stuck. Or you can configure it to drop the data and give you back an error, right? And so you control that. For some applications, what you really want to do is block, because you have the ability to block. For some applications, this is actually like data coming in from your users or something, and you can't tell them to like block because they don't listen to you that way or whatever. And your only ability is to like, you know, give some error. So you control that setting, and which you set would depend on the use case. Does that make sense? Cool. Yeah. Okay, so the question is, why is it called Kafka? There are several answers to that. One was we were moving off of a Harry Potter theme, which was Voldemort and Azkaban, something called Hagrid. There was probably like 7 or 8 Harry Potter things. But we kind of really exhausted good Harry Potter names at that point. And we were getting, you know, it was going to be like Snape or something really not very good. And so we switched over to writers. And so we had like a Kafka and a Camus. I think we have a couple others. I forgot. The second thing was we thought, well, okay, it's a system which is effectively keeping a log. And the other word for that is a journal. And so it's like it's a system for writing, which is kind of like a bad pun. And then we thought that like this whole picture, where was my horrible picture? This is kind of like Kafka-esque, right? It's Kafka-esque. So then you replace it with Kafka. I don't know. It's not a very clear answer. But that's what it's called. It's memorable. All right. Thanks everyone. I'm happy to take a few questions offline.